It is my opinion that the major problem with the understanding of the universe and cosmology, and in terms of physics and relativity and quantum mechanics, etc., is the problem is with the language. So it seems like everyone is using a different language, but in fact they are saying, could potentially be saying the same thing. And so what I want to do here is I want to take a few steps back and talk about the math. It seems like I'm getting messages from people that give me the feeling that that even the math underlying all of these fields is either misunderstood or is being said incorrectly or interpreted maybe incorrectly. And so what I want to do here is I want to take a few steps back and just look at the math itself right from first principles. So there are some people out there that I think maybe they don't think they're good at math, and maybe they are afraid. I don't want them to be afraid to watch my videos because they don't think they're good at math. I'm going to start from the beginning, and I'm going to give you my take on how math should be taught. Okay, I don't think math is being taught correctly, or maybe the best way that it could be taught, and so I'm going to teach it the way I would teach it if I was a teacher, and hopefully that will clear a few things up, and that some people out there that maybe are a little bit afraid of math, maybe they don't want to watch my videos because I'm bringing up too much math lately. Hopefully this will help them out. So what I did was a little thought experiment, and what I thought was, so what would happen if an alien came from another planet and they wanted to be able to describe their cosmology to us? But their language is completely different than our language. We would have to teach them our language because our symbols and our scribbles would not make any sense to them, and vice versa. So I did a little thought experiment myself and thought, okay, so if I was face to face with an alien and I wanted to understand their cosmology, I would want them to be able to teach me what they know or what they think they know. And so I did this little thought experiment, and this is what I would do in order to begin communicating with them. So the first thing they would need to know is how we represent our numbers. So without numbers, without a number system, we cannot be doing math. And so the first thing I would do is, first of all, I would show them my 10 fingers. I would show them my 10 fingers because we mostly deal in base 10 in our society, and so I would hold up my 10 fingers and I would show them that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 digits in our number system. And so these are the 10 digits that we have, and when we write a circle, we mean 0, and 0 means nothing. Okay, 0 means 0 things. 1 means one thing. This symbol here means 2 things. This symbol here means 3 things, and so on. Okay, so I think right away the alien would know exactly what I was talking about here. They would see 3 things here, and they would see this symbol, and they would understand that this symbol here meant 3 things. So next I would probably show them something like this. So they can see here that we have 10 unique digits representing our digital system, our digit system, and it goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I would show them, they would need to know some of our operators. They would need to know some of our symbols for addition, subtraction, multiplication, division. They would need to know what an equal sign is. So I would show them something like this, where I would say, 9 plus 1 equals 10. So they could automatically see that this symbol must mean add, because this plus this equals this. And they could see that 9 plus 1 equals 10. So the other thing this does is it shows the wraparound of our system. So we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 0, 1, 1. So that's what I'm showing here. So then I go, this new number 10 with 2 digits. The symbol for add plus 1 is equal to 11. And so all of this information here should be enough to give them a sense of our counting system, where we have a wraparound after 9 that goes to 10, 1, 0, and then 1, 1, and then 1, 2, and then 1, 3. So I'm pretty sure that an alien from another planet is going to have a similar thing in their language, and so I think right away they would be able to recognize what is going on here. So this page here gives them the digits that we have in our number system and the wraparound. So when you go past the 9th digit, now you need 2 digits to represent the number, and then and so on from there. And so we also have the equal sign here, so then they would know that this symbol here means that this operation here is equal to this, and I'm quite sure that an alien from another planet would have in the concept of an equal, and they would have a symbol for that we have for the equal sign. So this is basically the addition operation. So next I would have to teach them about subtraction. And so in subtraction we have the minus sign symbol here, and so this is the symbol of that we call minus, negative, take away. There's lots of ways of saying this, but basically from here they can see that 9 minus 1 equals 8, 9 minus 2 equals 7. So this should be enough information to give them the sense of what this symbol means. So that is the subtraction operation and the negative symbol. So next I would have to teach them about the multiplication symbol, the operation of multiplication. And so again I give two examples, and the first one is 2 times 3 equals 6. Okay, and I put this one in here as well. 9 times 1 equals 9. So this gives us two things. It gives us the multiplication operation plus the idea that this one here is the identity of the number system. So a number times the number 1 is going to give you back the number. So now, I have given them quite a bit of information about our number system and about the symbols that we use for the digits and the symbols that we use for mathematical operations. So the next thing I would do is I would draw a line on the page with an arrow on each end, and then I would lay the numbers down on the line, and this is what we refer to as the number line. So we call this the number line. It's also referred to as the real axis, and these are referred to as real numbers. But the aliens do it a little differently. The aliens call these primordial numbers. Okay, so the numbers are just the digits, and the digits can be combined into higher order numbers, and they refer to those as primordial numbers. And you've got positive primordial numbers and negative primordial numbers, and they refer to this axis as the primordial axis. Okay, so this is the first axis that we can define a number system on. So in a way, the aliens are decoupling the concept of numbers from the concept of an axis, because numbers can be used as quantities of things like counting money, and not necessarily used as positions or directions as you would be using on a number line. So they kind of decouple the numbers, the primordial numbers, from the primordial axis. And the reason we do this is because primordial, we're going to eventually have another axis, and so the primordial numbers are the numbers that are associated with any axis, not just the real axis. Okay, so I like that terminology, so I'm going to use that terminology when it becomes necessary to talk about these different axes. Also, the aliens have use the vertical direction for their primordial axis. So us humans, we were using the horizontal orientation for the primordial axis, which we call the real axis, and the aliens use a vertical line for their primordial axis, and they have negative going up and they have positive going down. Okay, so that's their convention on their planet. Fractal Woman from Planet Budabrot told me that this was their convention, and of course it's a different convention than what we have. It is rotated, so if you took this axis and rotated it 90 degrees so that this was vertical, then you would end up with this. And so they're just taking this, and they have a different convention where they want the negative numbers to be up and the positive numbers to be down. And the reason they do that is because they use the Mandelbrot set as a teaching tool. And so in the Mandelbrot set, this is the primordial axis is right here. Okay, right in the middle, and this is negative, the negative direction going this way, and the positive direction going this way, and the 0 point is exactly right here. And so the reason the aliens use this convention is because it's they can use then the Mandelbrot set as a teaching tool to help people remember the correct orientation of each of the individual axes. Okay. The other thing I want to point out to you is this number line is actually has no thickness. Okay, it's actually very, very, very thin. In fact, it's got no thickness at all, so you can't even say that it's thin. Okay, I have to, in order to draw this line on a piece of paper so you can see it, I have to give it some thickness, but this line definitely has no thickness. Now, what does that mean? That means that, okay, I'm going to give you an example, and I'm going to do it in the orientation that the aliens prefer, that Fractal Woman prefers. Okay, so here is the infinitely thin primordial number line, right? The primordial axis. And I'm going to put a little, here I put a little character on the line. Now this character, this animal, let's call it an animal. This animal is infinitely thin as well. It has no thickness, but it does have length. Okay, it sits on the primordial number line, and it's got some thickness. And so what can this little guy do? Well, the only thing this little guy can do is move up or move down. Okay, that's all it can do. If it's going to move, it can sit still too. Or if it moves, it can move up and it can move down. But what it can't do, what this guy can't do, is it cannot rotate. Okay, it can't rotate because this is the universe right here. This is the there is nothing out here, there is nothing out here, there's nothing to rotate into mathematically, and so there is no other axis with which to reference. And so this guy, and there's just nothing out here, it just can't do this. It can't do it. And so so the only thing it could do is go this way or go this way. So what I'm trying to say here is in the primordial number system, there cannot be a concept of rotation. Okay, you cannot have a concept of rotation. So the rules for the primordial number line are very simple. You can get bigger. Okay, you can get bigger. You can get smaller. You can move this way, and you can move this way. But you cannot do this because there is no other axis yet. We're going to be inventing one or introducing one, but without any other reference axes in the real number system, in the primordial number system, the rules are very limited. So primordial numbers and the primordial axis together form what I refer to as one-dimensional numbers. And in one-dimensional numbers, you cannot have the concept of rotation, but you can have the concept of polarization. So you can see, because you have arrows going in two different directions, you can have the concept of polarization. And so this could also be referred to as the domain of polarization. And as we know, polarization plays a key role in a lot of the physics that we are trying to understand. And so we've got, magnetic dipoles or polarization, electric dipoles. The pole means polarization. And so the domain, the primordial numbers, or the one-dimensional numbers, are the domain of polarization. So this is where the aliens stepped in and taught me about two-dimensional numbers. So this is the language that they use to implement their two-dimensional numbers. And so, of course, one-dimensional numbers, you have one value in a box, in a container, one value, which can be any value. The star is just a primordial number, and that can be a whole number, that can be a decimal number, that could be the number pi. It can be any value, any ponderable value that you can write down, positive or negative, is a primordial number. So but with primordial numbers alone, with the one-dimensional numbers alone, you cannot define an angle, therefore you cannot define rotation. And so you need two-dimensional numbers in order to be able to define a rotation. And so two-dimensional numbers look like this. Okay, it is a 2x2 matrix, and each entry into this matrix is a primordial number, and it can be any value. It can be 0, it can be 1, it can be pi, it can be pi over 2, it can be the sine of pi over 2, any value that you can write down in here. It could be a rational number or an irrational number, would go into these 4 entries. So if you are drawing a graph that looks like this, and you place a point here, and you call that x comma y, you are in the domain of two-dimensional numbers, whether you realize it or not. So in the language of the aliens, the x-axis, what you would normally call the x-axis, what you would normally call the real axis, they refer to as the primary axis. And the axis, the y-axis, which is 90 degrees orthogonal to the primary axis, is they call the secondary axis. Okay, and just to complicate things further, the aliens put the primordial axis on the vertical, and they put the secondary axis in the horizontal, which we call imaginary. And so this is the real axis, this is the imaginary axis in the Mandelbrot set, and of course without two-dimensional numbers, the Mandelbrot set would be impossible to draw. So you need at least two-dimensional numbers. You need exactly two-dimensional numbers to generate the Mandelbrot set. And this is the primary axis, the real axis, and this is the secondary axis, horizontal, which humans on Earth refer to as the imaginary numbers. So the aliens don't use the term real and imaginary. They use primary and secondary. They don't think it's right to attach words that have sort of arbitrary meaning or some other meaning that might be misinterpreted, especially when you're talking about math. And so they use primary and secondary for these axes, and they are rotated 90 degrees clockwise from what humans do. But I'm going to leave our convention just because I think it'll be less confusing that way. So horizontal is still is primary, what you call real, and vertical is secondary, what you call imaginary. So in order to work with two-dimensional numbers, you're going to need to know how to do arithmetic with two-dimensional numbers. And so what I'm going to show you here is how to add two-dimensional numbers, how to add 2 by 2 matrices. And so that's pretty trivial. I'm going to add this 2 by 2 matrix to this 2 by 2 matrix, and basically what you do is you take the first element of the first matrix and add it to the first element of the second matrix and put that into the first element of the third matrix, the upper left corner. And so then you, for each element, you do the same thing. So you got B plus F and put that into the upper right quadrant. And then you take the lower left quadrant and you go C plus G and you put that into the lower left quadrant. And then you go D plus H and you put that into the lower right quadrant. So each quadrant gets added to the same quadrant in the other matrix and placed into the same quadrant in the 2 by 2 matrix. So that's fairly trivial, but I think it's important to look at it anyways. This is how you add two-dimensional numbers. So next we're going to multiply two-dimensional numbers, and to do that it's a little trickier. Okay, doing multiplication of 2 by 2 matrices is not trivial, but I'm going to show you how to do it, and this is something for sure you're going to have to practice. Okay, so what you do is you are going to be multiplying the row of this matrix to the column of this matrix. So if you want to multiply this matrix to this matrix, this is what you do. And so I'm going to highlight the column of this matrix, and what you're going to do is you're going to go A times E plus B times G, and you're going to put that into the upper left quadrant here. So you're going to take E, so A, the first coordinate here, the first row column here, A times E plus B times G, and that all gets packed into the upper left quadrant of the 2 by 2 matrix. And then what you're going to do is you're going to do the same thing, only you're going to do it to these two parts in the matrix. So you're going to go C times E plus D times G, and you're going to put that down here in the lower left quadrant. So you're getting the upper left quadrant of the answer and the lower left quadrant, and here's the answer. Okay, so then to get the results for the right hand side of this 2 by 2 matrix, you're going to be using this column. So you're going to multiply this column through this matrix. So you're going to go A times F plus B times H, and you're going to put that in here. And then you're going to do that with the bottom here. You're going to multiply that by that, so you're going to go C times F plus D times H, and you're going to put the answer right there. So as you can see, this is a little more complicated than doing addition, and so this is going to take some practice before you can do it naturally, but it is fairly trivial in the sense that it is not it's not calculus. But this is something you could definitely practice and get good at, and if you got good at doing this, it is going to be very helpful in solving complicated problems that involve two-dimensional numbers. So here's a very simple example, but this should help you maybe visualize this a little better. So to multiply this two-dimensional number by this two-dimensional number, you go 1 times 5 plus 2 times 7, so you're multiplying the row by the column. So 1 times 5 plus 2 times 7, and then you put that in here. And then you do 3 times 5 plus 4 times 7, and you put that here. And then so that takes care of the left column. So you'll multiply the left column by this row and this row. And then you generated this column in the answer. And then we do the second column. Okay, so we go 1 times 6 plus 2 times 8, and you put the answer here. And then you go, you do the bottom here, so you go 3 times 6 plus 4 times 8, and you put that in this quadrant here. And then when you add all these up, you do it in your head because these numbers aren't very big, and you get the answer is a 2 by 2 matrix, 19, 22, 43, and 50. And so this is how you multiply 2 by 2 matrices together. I wrote a computer program to do it, so I don't have to always remember how to do this. I would just pump it through my multiply matrix function and get out a 2 by 2 matrix. So this is super simple in my opinion. In order to be able to do math with two-dimensional numbers, you really only need to be able to know how to add and how to multiply. You only need to know how to add and multiply, and then you have to learn how to add and multiply two-dimensional numbers, which for adding is very trivial, and for multiplying is a little more complicated, but you just have to understand the procedure. You have to practice the procedure to make sure that you're multiplying the right thing by the right thing and adding the right thing to the right thing to get the right answer. And so this is definitely super simple in my opinion. Multiplying, doing arithmetic in 2 dimensions using two-dimensional numbers is not that bad. So complex numbers are also two-dimensional numbers. They can be represented in a 2 by 2 array, only they have a few extra rules attached to them. And the rule is that the forward diagonal of the 2 by 2 matrix must have the same sense. So if this is positive, let me just put a plus there, then this must be positive. And if this is negative, this has to be negative. And if this is positive, this has to be negative. And if this is positive, then this has to be negative. Okay, so these are the rules of complex numbers. I'm going to go back to my original. Okay, so normally I write the matrix with positive on the forward diagonal and positive in the upper quadrant and negative in the lower left quadrant, but in reality A and B can be both positive and negative numbers. So if B is positive here, it has to be negative here, and if B is positive here, it has to be negative here. And so these are the complex numbers implemented as a 2 by 2 matrix. And so what I'm going to do is, so the interesting thing about complex numbers, well, about two-dimensional numbers I should say, is when you add and multiply matrices together, that multiplication procedure is doing the algebra for you. Okay, so if you already know how to multiply 2 by 2 matrices, then you actually could do a lot of high-end scientific work without even doing any algebra. And I'm going to show you what I mean. So what we're going to do is we're going to square this number. We're going to multiply this two-dimensional number by itself using the rules of multiplying two-dimensional numbers. Okay, so so we start with multiplying the column here with the row here. Okay, so we've got A times A times A, okay, plus B times minus B, right? So B times minus B is minus BB, so it's A times A minus B times B, okay, because a positive times a negative gives you a negative value. So then we're going to, so that fills in that quadrant. So now we're going to do this quadrant here. So we're going to multiply this column by this row. So we have minus b times a, or minus ab, plus, okay, this is where it gets a little tricky, plus a times minus b, which is minus ab. Okay, so we have minus ab, and then we have that quadrant. Okay. So now we are going to multiply this column with this row here. So what we have is a times b plus b times a plus a times b. So now we have this quadrant here. And so finally we're going to multiply this column with the bottom row here. So we end up with a b times minus b, which is minus bb, and an a times a. So we have a times a minus b times b in here. Okay, and so I'm going to write it a little differently. So we've got on the forward diagonal, we've got a squared minus b squared, a squared minus b squared, and on the backward diagonal we have 2ab and minus 2ab. So we have another complex number. So multiplying two complex numbers together gives you another complex number. And as you can see, it kind of did the algebra for you. Okay, this is what algebra really is under the hood. It is matrix multiplication, and so this is, you basically just did the FOIL rule, the FOIL rule that you would do when you're doing algebra and you are multiplying two two-dimensional numbers together, basically. Only we are doing it, this is the most transparent way of doing two-dimensional numbers, of doing algebra. This is literally algebra what we're doing, but we are noticing that two-dimensional numbers could and should be represented by 2x2 matrices. And when you practice and learn how to multiply 2x2 matrices together and get an intuition about it, then you basically don't really have to do the algebra, because you don't have to know the algebra necessarily, because the matrix multiplication does the math for you. And so the main reason I became interested in complex numbers is because of the Mandelbrot set, the Mandelbrot fractal. This fractal pattern literally lives in the domain of the two-dimensional numbers, of the complex numbers. Okay, the complex numbers with the special rules of the forward diagonal having the same sense and the backward diagonal having opposite sense. Okay, so I learned complex numbers from the Mandelbrot set. So I didn't learn it in school. I don't remember getting taught it in school, even in university when I was doing computer science. Maybe if I went on to further my education, I would have learned about complex numbers, but I'm pretty sure they would have confused me more than anything. And so I'm glad I learned complex numbers from the Mandelbrot set. And in terms of the two-dimensional representation of complex numbers, I actually learned that from Robert Distinti. So Robert Distinti is the one that gave me the right clues as to how to implement complex numbers in a 2x2 matrix form. And so I would highly recommend you go watch his videos. This was a huge, sort of a breakthrough in my thinking on complex numbers, especially in the fact that I was able to apply them directly to the Mandelbrot fractal and generate this using the 2x2 matrices, and having the matrix math do the algebra for me. And so this was, a nice sort of surprise for me, and it really helped me further understand, maybe get a better intuition of what is going on with this guy under the hood. So I hope this video has helped those out there that maybe don't think they're good at math, or maybe a little bit afraid at math, or maybe they're a little bit afraid to watch my videos. I highly recommend that you practice multiplying two-dimensional numbers just to give you the confidence to make you to give you the sensation that you can that you shouldn't be afraid of math, that you can do math. And if you can multiply 2 by 2 matrices together, if you can add and multiply them and do it you know, with confidence, then you will be surprised at what you can accomplish with these numbers without even having to know very much algebra. You can do a lot with these with the two-dimensional representation of complex numbers, and so which I've shown in many videos. And so there's a, you know, even in electronics, they use it in electronics, they use it in quantum mechanics, they use it in relativity. And so it's my feeling that complex numbers as 2 by 2 numbers, if we sort of re-implement everything using two-dimensional numbers, using the 2 by 2 representation of complex numbers, that we might get a better intuition of what is going on under the hood in quantum mechanics and relativity, and maybe even unify those languages. We may even be able to unify those languages by re-implementing them, by reanalyzing them, by reinterpreting them from the perspective of the 2 by 2 matrix form of the complex number. So that is what I'm thinking. If it's possible, I mean, this is what I'm working towards, and if anyone out there wants to help me see if we can make any improvements to the language by using this form of the complex numbers, I would be happy to support that. And so that's all I'm going to say for today. I hope you had a good weekend. I know I did. And well, I'll be back.